This video has to do with the first part of the discussion about the Bernoulli equation. The Bernoulli equation is one of the oldest equations that is used in the field of fluid mechanics. It's for their applications to the case where there is fluid flow. That is, we no longer are considering the situation of static conditions. You'll recall that for static conditions, the fluid is not in motion relative to the container that it's in. In the case of dynamics, the fluid can move relative to the container, and in general there would be shear stresses associated with that. We'll find that in the application for the Bernoulli equation, we'll make the assumption that the shear stresses are zero, and that somewhat simplifies the problem, and we'll find that for many cases this is a good enough assumption to make to solve certain types of problems. We'll get into the subject of shear stress, energy loss as a result of shear stress, and that sort of thing in later chapters. So the chapter objectives are to apply Newton's second law to fluid flows, to derive Bernoulli's equation, understand its uses and limitations, apply the Bernoulli equation to simple flow problems, apply concepts of static, stagnation, dynamic, and total pressures. That is, you should be able to define what those four types of pressures are, or those four definitions of pressure, be able to calculate them, and then to calculate flow properties, or let's say flow characteristics, using energy grade line and hydraulic grade lines. Now, there are many cases that we've already seen when fluids are at rest relative to their container, or basically where the fluid might be in motion, but it's in rigid body motion, such that it's not in motion relative to its container. And so for those cases, hydrostatic conditions apply. But in situations where the fluid is moving relative to the container, in those conditions, hydrostatic conditions may not apply. So what we're going to do here in the derivation of the Bernoulli equation, we're going to make the assumption is that there is no viscous force. We'll assume that the fluid is inviscid, that is, that the viscosity, usually referred to as mu, the dynamic viscosity, or nu, which is the kinematic viscosity, is assumed to be zero. And for these situations, we'll be defining in a later chapter that the flow is what's called irrotational. We'll also make the assumption that the flow is steady. That's different from equilibrium or static conditions. In this case, the flow is in steady motion, but that is that the fluid is not stationary. Essentially, when we say it's steady, that there's no change in any of the fluid parameters such as pressure, or fluid variables such as pressure and velocity, as a function of time. So at any given location in a moving fluid, it's for steady state flow conditions, the pressure at that point, the velocity at that point, the density, temperature, all different variables associated with the fluid flow will be constant as a function of time. And as I mentioned before, the equation that we'll be deriving here is one of the oldest equations used in fluid mechanics, the Bernoulli equation. So let's look at the geometry of flow, and for this we'll consider pathways that are taken by fluid packets or fluid particles, and these pathways can be looked at as being what are called streamlines, or path lines, as we'll define in later chapters. And what we'll find is that streamlines provide for a coordinate system for the natural flow that's occurring to describe the motion of the fluid. So if you look here at the figure, part A, we see an object, the very dark black object in the lower right hand corner of that figure. The fluid is moving around that object because it cannot penetrate through the object. So the fluid is moving from the left to the right. It passes around. And you'll see the blue line with the arrows, which indicates the pathway that a particular particle that starts at, let's say, point 1 will move along as it passes around the particle. That particle or that fluid packet will move from point 1 along that blue line and will pass through point 2 and on to the right hand side. You could also consider the situation where maybe a fluid packet might be moving in the lower left hand corner, let's say at this point right here. That fluid particle or packet is going to move along this dark line here. That's a streamline, and it will move down underneath the particle. So those are pathways, or you could say they are streamlines, and we'll define those in much more greater detail at a later time. But the understanding of a streamline is important in the application of Bernoulli's equation. So we define it early on, and later chapters will go in much more detail about path lines, streamlines, streak lines, and other types of definitions like that. If we look at the figure part B, or figure B on the right hand side, we'll see we've isolated some of these streamlines. And one of the things that we do is that the streamline does provide for a natural coordinate system. If we go along that streamline, we have a coordinate that goes along the line. We'll call that coordinate S. It starts at a certain origin. What you see here is being this dot. That's an arbitrary location along the streamline and moves along that, and the distance that you travel is S. And then there's a normal to that, unit normal, coordinate system given by n, and that's perpendicular to the streamline at any given point, or you could say it's orthogonal to that streamline at any given point. And we could draw this coordinate system for any one of the streamlines that you see in the figure. Normal to the streamline we define here, and we'll use this later, we define a radius of curvature of the streamline, and that's just measuring how much bending, you might say, occurs in the streamline. And in this figure, the amount of bending is very much variable as you pass along the streamline. On the left hand side, the streamline is fairly straight at that along in here. If we were to draw a radius of curvature, basically if the line is straight, the radius of curvature would be infinite. Capital R would be equal to infinity. As we pass from the left to the right, going along that streamline, the streamline here where you see the R is being defined here, that streamline, at that point the streamline is somewhat curved, and so the radius of curvature is finite as shown. And then as we pass further along, the streamline starts to bend. Instead of bending up, it now starts to bend down. In that case, the radius of curvature would be defined on the other side, but it is curved. So wherever a streamline is straight, the radius of curvature will be infinite. The more tight or the more bent that streamline is, the smaller or the more finite the value of the radius of curvature. So we're going to use both the distance S, a distance n perpendicular to the streamline, and the radius of curvature in our definitions. We also will, or I should say in our derivation of the Bernoulli equation, we also have the velocity v, which is the velocity of the fluid packet as it passes along the streamline, along the axis of the streamline in the S direction. Here there is no velocity v normal to the streamline. It only acts along the streamline. Alright, so if we look here on the next figure showing this image of this glider and a streamline passing over the wing of the glider, there's various forces that are acting on the fluid packet. So we've isolated the fluid packet, as you can see on the right hand side. The newer version of the textbook has the correct orientation of force F4, which should be normal to the packet. And so I've kind of scribbled out the other arrow that's shown there. So the version of the text that you have should have that force F4 being normal or perpendicular to the fluid packet. On the fluid packet, within the two-dimensional plane that's shown, we have the forces, pressure forces that are acting on the upstream and downstream side of the fluid packet. That is F1 and F2, or sorry, F1 and F5 are acting along the axis of the streamline. We also have forces, pressure forces that are acting on the, you might say, the sides of the packet in the N or the normal direction. Those are the forces F4 and F2. And in addition to that, we have the gravitational force acting on the packet, which is given as F3. And that gravitational force has a component that's in the along the axis S of the streamline and also normal to the streamline. So we can decompose the force F3 into two parts, one that's parallel to the streamline and one that's normal to the streamline. The breaking down of that force into those two components depends on the angle theta, how much, what the orientation of the streamline is at any given point. Oh, and I'll mention here, sorry, that other forces are actually neglected here. Viscosity, we said that the fluid is inviscid, so we're neglecting the viscosity, and we also are neglecting the force of surface tension. They could be considered, but not in the derivation of the Bernoulli equation. So let's look at the packet itself. This diagram actually illustrates more closely all these forces, and what we're deriving here is the Bernoulli equation, what's considered to be the classical Bernoulli equation, which is the equation for, you might say, the energy of flow along the streamline in the S coordinate direction. So if you look at this packet, we've broken down the forces into pressure forces that are acting on the surfaces. And if we look at the pressure forces on the upstream and downstream side of the end of the packet, we see on the left-hand side a pressure on the left-hand side, which is P, minus a increment in pressure, delta PS. That is the pressure that's acting in the S direction. And that's multiplied by the surface area of the packet on the left-hand side, which has a size of delta N in the normal to the streamline, and then delta Y would be the coordinate, let's say, into the perpendicular two-dimensional plane. You might say into the paper or into the image that we see here. On the downstream side of the packet, we've got pressure, which is P plus the delta PS. Now, delta PS is just a change in the pressure as you go from one end of the packet to the other end. So there's a finite change in that pressure, and that's what's defined here. So the pressure P is the pressure at the center of the packet. One is on the upstream end, it's slightly less pressure. On the other end, the pressure is slightly greater, P plus delta PS. And that also is multiplied by the cross-sectional area of the packet on the downstream end. When you do that multiplication, you get a total force, pressure force that's acting on the upstream and the downstream side of the packet. The other force that we're looking at here, again we're looking at only the forces in the S coordinate direction here, would be the component of the weight that is acting along the coordinate of the streamline, and that force is delta WS. So we take the force delta W, and we're looking only at the component that's in the S direction, which is delta WS. So if the angle theta is 0, then delta WS, of course, would be equal to 0, because the packet would be moving horizontally. We'll neglect the forces that are acting perpendicular to the packet, because those will be used in another analysis to derive another Bernoulli type equation, but it will not be for flow along the streamline. It will be for conditions normal to the streamline. I'll mention here, you can see that we've neglected the shear forces, because generally there would be a shear force on the surface of the packet, tau delta S delta Y, because generally these packets won't be all moving at the same velocity. So if they're moving at different velocities, and if there is some viscosity, then there would be some shear stress. But here we're neglecting that shear stress in the derivation of the Bernoulli equation. Alright, so basically what we do is we take this force that's on the upstream and the force on the downstream, and then this gravitational force, and we're going to do a sum of forces in the S direction. One's acting to the right, one's acting to the left. Actually, two of them appear, at least in the definition given here. They're acting to the left. The sum of those forces should be equal to 0 if you have static conditions. If we have dynamic conditions, if there's a net force, then there'll be an acceleration. So we take those forces, we sum them, and that's what's given here. That term on the left-hand side is the sum of the pressure forces and the gravitational force. This part here is the gravitational force. This part here is the pressure force. And if those were balancing each other, if there was no change in the pressure in the downstream direction or along the S coordinate, if there's no gravitational force, then, or at least if those balanced each other, then you would have hydrostatic conditions, and the acceleration would be 0. If they are not the same, then you have a net force acting on the body in the S direction, and that would then, of course, cause acceleration, according to the Bernoulli. According to Newton's law, F is equal to m, the mass times the acceleration a. That this is the net force, which we could say is the force that's there, and ma would be the mass times the acceleration. That's what this is. This is the acceleration in the S direction. Rho is the unit density of the fluid. That acceleration is the same thing as rho times the velocity of the packet times the rate of change of the packet, rate of change of the velocity of the packet in the S direction. That is the definition of the acceleration. Alright, so we can take that equation. All the terms are given as a function of S, that is, the derivatives are with respect to the coordinate direction S. We can now integrate that equation by in the direction S, that is, we can do a integral something, all this stuff that's there, ds. And if we do that, we end up with what's called the Bernoulli equation. Bernoulli equation says that the pressure plus 1/2 rho v squared plus gamma z is equal to a constant along a streamline. Alright, so if you pick out a streamline in a flow, the packet's moving along that, all packets are moving along that streamline. Any packet that passes through one point in the streamline will pass through all other points in the streamline. If we know the pressure at a given point in the streamline, so let's say that I pick out a streamline that's moving like this. This is some point here. We define the pressure at this point. We define the velocity at that point. We define the elevation at that point. We can substitute those numbers into the above equation, into this Bernoulli equation here. If we do that, We sum those numbers together, we'll get a constant C1. That sum that we see there will be a constant all the way along that streamline, S. And what would vary then as we go along S would be possibly the velocity, possibly the elevation, possibly the pressure. But we know that the combination of those three variables given on the left-hand side of that equation has to always sum to be equal to the constant that we determined at this point right there. Now, I do that at that point, or I define it at an arbitrary point where I can make the measurement of the pressure, velocity, and the elevation, and I'm confident then every other location that a particle passes through along that streamline, every other point, that the sum of those numbers will always be equal to that constant, even if those numbers change as they move along the streamline. This is a powerful equation because it allows us to look at the dynamics of flow. As elevation changes, there can then be a pressure change and a velocity change, and we can completely calculate unknown quantities by just having enough information about some known quantities along the streamline. We'll see a lot of applications of this for different types of flow conditions. The other equation that's kind of like a Bernoulli equation, it's less commonly used. Usually the Bernoulli equation is the one we want to use, but the other one would be to look at what's happening normal to a streamline. We may be interested to know how the velocity or the pressure varies normal to a streamline. So here we go back, look at the streamline again with the packet, and now what we've got, again, we're making the assumption that the shear stress forces are zero, but we'll look at these forces. Here, this pressure force right here, this pressure force right here, this weight force right there. And we're going to do a vector sum of those, the sum of the forces in the in the n direction, normal to the streamline. The sum of those should be equal to zero if we have hydrostatic conditions. If we don't have hydrostatic conditions, that is, if those forces do not sum up equal to zero, there must be something that's going on. There must be some acceleration. And this will occur, there will be acceleration if the streamline has a bend to it, that is, if there's a curvature to it. Remember I said that the radius of curvature is infinite if the streamline is straight. In that case, there will be no bend in the streamline and there will be no acceleration normal to the streamline. But in the case where the streamline is bent, there is a acceleration in the flow. Even if the velocity along the streamline remains constant, if the streamline is bent, that is, if the direction of the flow is changing, which would happen if the streamline is bent or curved, there is acceleration, because acceleration is defined either as being a change in magnitude of the velocity or a change in direction of the velocity. Alright, so if we take these forces normal to the streamline, we can sum those forces, and those are given on the left-hand side of the equation, just as we saw for the Bernoulli equation. Sum of the pressure forces, sum of the weight force. If those are not balanced, then they have to you have to have a acceleration of the fluid, and that acceleration in this case, you might think of it as being centrifugal force that's acting on the packet as it's moving along the streamline in a curved fashion. That acceleration is given by rho an, where the an is the acceleration normal to the streamline, and this is a centrifugal acceleration, centrifugal force, you might think of that being. So here that force is proportional to the velocity along the streamline divided by the radius of curvature. If the streamline is straight, then r is infinite, and that rho v squared over r will be 0. There will be no acceleration. But if there's a curvature to the streamline, then the acceleration will be non-zero, because r becomes smaller and smaller as the bending in the streamline becomes greater and greater. All right, so make the assumption that we have constant density. We can do the integration of that equation, but now the integration is of some stuff here in the parentheses, dn. So we're integrating in the normal direction to the streamline. That ends up giving us the equation here, which basically says that along the normal at any given point, if you start from the streamline, normal to the streamline, you move normal to it either above or below the streamline. The pressure plus the integral term plus the elevation term times gamma, that will be equal to a constant C2. So at the point of the streamline, we could define the pressure plus the integral term plus the elevation term, and that would give us this constant. And that constant will be defined, or will be a constant perpendicular to the streamline. Now, to make this evaluation, of course, you need to know what the velocity is along the streamline and normal to the streamline. You also have to know what the curvature of the streamline is. You need to know the radius of curvature at different points. This equation is much less used within fluid mechanics. We usually will see most of our applications are going to be using the Bernoulli equation. But there is some utility to this equation, and we'll show you some of that use at a later time. So the assumptions for the Bernoulli equation, just to review those, we assume that viscous effects are negligible. Flow is steady state, that is, the fluid is moving relative to its container, so we don't have hydrostatic conditions. But things do not change as a function of time. They only change maybe as a function of location. The fluid is assumed to be incompressible, that is, that the density is a constant. It's seen here that Bernoulli equation is applicable only along a streamline, because that's how it was defined. And then what we'll call the normal equation, which is like a Bernoulli equation, but it's applicable only normal to a streamline. All right, and we say that these two right here are assumptions, but basically they come about because that's how, when we derive them, we derive the Bernoulli equation for conditions along the streamline, and we derive this normal equation for conditions normal to the streamline. Now, there are various pressures that we'll define here, and you should be familiar with what these pressures are. And certainly the lab experiences that you'll have and other calculations you'll do, you'll use different types of pressures. So we'll define P here as being the static pressure. We'll define gamma Z as being the hydrostatic pressure. Those two terms appear in the Bernoulli equation, and they also appear in other equations that we looked at. We'll come up with rho v squared over 2, which is in the Bernoulli equation. We'll call that the dynamic pressure, and we'll see how that's applicable to certain fluid flow conditions. And then if we sum all those pressures together, if you see the first three pressures that are defined here, the static pressure, the hydrostatic pressure, and the dynamic pressure, they all appear in the Bernoulli equation for flow along a streamline. If you sum those three together, that's what we call the total pressure. All right, and we'll see what the definition of stagnation pressure is. Stagnation pressure occurs at what's called the stagnation point. It's a location, and we'll see the physical situation for that, so it'll be understood what that exactly means. But it's a pressure that develops, let's say, in a fluid flow at the point where the fluid is moving along, a packet is moving along, and suddenly it enters a location where the fluid velocity is 0. Maybe at a location where an object is that the fluid is running into, and suddenly it becomes stationary at that point. The pressure that exists there then is the stagnation pressure, and we'll define that later. So I'm going to end this video here, this first part, and we'll go on with the next video, next section of this video, carry on with that.